Take a grain of sand. Hold it at arm's length, that tiny patch of sky you just blocked. The James Webb Telescope pointed at that exact spot for 12.5 hours. What it captured will break your brain. Over 25,000 galaxies, not stars, entire galaxies. Each one contains billions of suns, planets, maybe life. The light from the farthest ones traveled 13 billion years, back when the universe was a newborn. If this doesn't make you hit subscribe, nothing will, because what you're about to see doesn't just shrink our solar system. It fundamentally rewires what it means to exist, and we're just getting started. Prepare yourselves. We begin. Floating 1.5 million kilometers from Earth, at a gravitational balance point called the second Lagrange point, where the pull of our planet and the Sun cancel each other into perfect equilibrium, the James Webb Space Telescope watches the universe with an eye that fundamentally rewrites the rules of seeing. A machine so sophisticated that calling it a telescope feels like calling the internet a filing cabinet, because this observatory doesn't merely magnify distant objects. It captures ancient light that has traveled for over 13 billion years, light that began its journey when the universe was less than 4% of its current age. And to achieve this impossible task, Webb carries a primary mirror that stretches 6.5 meters across, a golden honeycomb of 18 separate hexagonal segments made of beryllium, a metal both lightweight and incredibly strong, each segment coated with a layer of gold thinner than a human hair, yet perfectly engineered to reflect infrared light with maximum efficiency, giving the telescope a total collecting area of 25.4 square meters, more than 100 times more powerful than the Hubble Space Telescope in certain observations. And this mirror had to be folded like origami to fit inside the Ariane 5 rocket that launched it in December 2021, unfolding in space through a delicate ballet of more than 300 separate steps, each movement controlled by tiny motors called actuators that can adjust the mirror segments with nanometer precision, movements smaller than the width of a single strand of DNA, ensuring that all 18 pieces align to form a single perfect surface capable of focusing light with extraordinary accuracy. While behind this shimmering golden mirror sits a suite of 4 scientific instruments, so sensitive they can detect the faintest heat signatures from the first galaxies that ever formed. Instruments that must be kept colder than anything naturally occurring in the solar system, protected by a sun shield the size of a tennis court, 22 meters long and 12 meters wide, made of 5 thin layers of Kapton material, coated with aluminum and silicon, each layer separated by precise gaps that reduce the temperature between the hot side facing the sun, which can reach nearly boiling point, and the cold side where the instruments operate at 45 Kelvin, minus 380 degrees Fahrenheit, a temperature so extreme that it would freeze air solid. And the mid-infrared instrument, or MIRI, must be even colder, cooled to 6 Kelvin, minus 267 degrees Celsius, minus 449 degrees Fahrenheit, just 7 degrees above absolute zero, the point where all molecular motion stops, achieved through a special cryocooler system that circulates helium gas in a continuous loop. And this entire observatory weighs 6,500 kilograms, with the spacecraft bus, a 350 kilogram structure made of graphite composite material, supporting the 6,200 kilogram telescope, and the whole assembly can point with a precision of 1 arcsecond, roughly the width of a human hair, seen from 20 meters away, while stabilizing vibrations to within 2 milliseconds. A level of steadiness that would be like keeping a laser pointer steady on a dime from over a kilometer away. And it does all this while orbiting the sun at tens of thousands of kilometers per hour, maintaining its position to within a few kilometers of the perfect Lagrange point. 4 times farther from Earth than the Moon, a location chosen because it allows the telescope to keep its massive sun shield constantly facing both the Sun and Earth, ensuring the instruments remain in permanent shadow and deep cold. And from this vantage point, Webb observes the universe not in visible light like Hubble, but in infrared wavelengths ranging from 0.6 to 27 microns, a region of the electromagnetic spectrum, invisible to human eyes, but crucial for seeing through cosmic dust clouds and detecting the red-shifted light from the most distant objects, light that has been stretched by the expansion of space itself, from visible wavelengths into the infrared. And this capability transforms Webb into a time machine, because when we look at the most distant galaxies in its images, we see them not as they are today, but as they were billions of years ago, when the universe was young and the first stars were igniting, and the telescope's near-infrared camera acts as its primary imager, capturing sharp pictures of distant galaxies, newborn stars, and exoplanets, while the near-infrared spectrograph breaks light into its component wavelengths like a prism, analyzing the chemical fingerprints of stars and galaxies to determine their composition, temperature, and motion. And it can observe more than 100 objects simultaneously using tiny mechanical shutters. And the mid-infrared instrument extends Webb's vision even deeper into the infrared, capturing light from the earliest galaxies and observing cooler objects like dust clouds where stars and planets are forming, as well as comets and asteroids in our own solar system. And the fine guidance sensor helps maintain the telescope's incredible pointing accuracy, while also studying exoplanets by analyzing how their light changes as they pass in front of their stars. And together these instruments allow Webb to perform an astonishing variety of tasks, from capturing images of the first galaxies that ever existed to studying the atmospheres of distant worlds that might harbor life. And the telescope communicates with Earth through NASA's Deep Space Network, sending back terabytes of data every day, high-resolution images and spectral data that teams of scientists around the world analyze to make new discoveries. And every image Webb produces represents countless calculations, alignments, and data corrections, because the colors we see are not what the telescope sees directly, but are created by translating infrared light into visible colors, so human eyes can appreciate the hidden beauty of the cosmos. And this translation reveals stories of distant galaxies colliding, stars being born, and planets circling alien suns. And Webb's ability to see farther and deeper does not simply mean greater distance, it means revealing more layers of the universe's history and structure, peeling back another layer of mystery with each observation, whether it is the faint afterglow of the first galaxies or the chemical traces of life in another world's atmosphere. And the telescope's mirrors contribute to this precision in a remarkable way. Each of the 18 segments, made of beryllium, polished and coated with gold, tested at cryogenic temperatures to ensure they hold their shape, and when assembled, they act as a single perfect mirror, reflecting light with extraordinary clarity. And because of these features, Webb can collect far more light than Hubble, making it over 100 times more powerful in certain observations, capable of spotting galaxies that are too faint for any other telescope, revealing how the universe transitioned from a dark, chaotic place into one filled with stars and galaxies. And this period, known as the Cosmic Dawn, has long been one of astronomy's greatest mysteries, and Webb is finally providing the evidence needed to understand it. And the telescope is not only looking outward in space, but also backward in time, capturing the story of how everything began, the slow formation of structure from the Big Bang, the creation of stars, and the assembly of galaxies. And every speck of light in its images is a world, a collection of billions of suns, each with its own history. And even within our solar system, Webb has begun to transform our view, studying the atmospheres of giant planets like Jupiter and Saturn, observing the icy moons of the outer planets, and detecting faint objects in the distant Kuiper belt, and its infrared vision reveals details that no other observatory can see, such as heat signatures, chemical compositions, and changes over time. And through all these achievements, the telescope stands as a symbol of what human beings can accomplish when they work together with patience and imagination. The product of over 3 decades of planning, testing, and persistence, with thousands of people from many countries contributing to its creation, from the engineers who built its delicate mirrors, to the scientists who designed its instruments, and the teams who guide it across the void of space. And the telescope's mission continues every day, sending back streams of data that help reshape our understanding of the cosmos. And each new observation adds another piece to the grand puzzle of existence. Whether it is revealing the first stars, uncovering new exoplanets, or studying the faint glow of ancient light, and the James Webb Space Telescope remains our greatest tool for exploring the unknown. A giant eye in space, forever gazing into the past to illuminate the future. And this is why Webb represents more than just an engineering marvel. It is humanity's most sophisticated attempt to answer the deepest questions we can ask. How did the first galaxies form? How did stars and planets begin? What are the conditions needed for life to emerge? And these are not just scientific questions, but deeply human ones, touching on our own origins and our place in the cosmos. And Webb's design includes technology to study planets outside our solar system in remarkable detail, using its spectrographs to analyze the light from distant exoplanets as they pass in front of their stars. And when starlight filters through a planet's atmosphere, it carries the fingerprints of the gases within it. And by studying these fingerprints, scientists can identify whether a planet has water vapor, carbon dioxide, methane, or other chemicals associated with life. And this ability opens an entirely new frontier in the search for habitable worlds. Because before Webb, most exoplanet studies focused on detecting planets and measuring their sizes or orbits. But now, for the first time, astronomers can study what those worlds are actually like, their weather, composition, and perhaps even whether they could support life. And Webb has already observed several known exoplanets and detected clear signs of water vapor and other atmospheric features, proving that its design exceeds expectations. And another fascinating part of Webb's mission involves studying the formation of stars and planetary systems, because inside giant clouds of gas and dust, new stars are born. But these regions are often hidden from view. Invisible light and infrared light, however, passes through the dust, revealing what is happening inside. And Webb can capture images of these star-forming nurseries in astonishing detail, showing how matter collapses under gravity to form stars, and how surrounding disks of gas and dust evolve into planets and beyond our own galaxy. Webb observes the large-scale structure of the universe, the cosmic web of galaxies, and dark matter that stretches across billions of light years. And by mapping these vast structures, astronomers can test theories about how gravity and dark energy have shaped the universe over time. And the telescope's ability to see faint galaxies from the distant past helps piece together a timeline of cosmic evolution, showing how small clumps of matter grew into the massive galaxies we see today. And to achieve all of this, Webb relies on precise engineering with a mirror alignment system that uses sensors and actuators that can move each segment by only a few nanometers, a scale so small that it would be like adjusting the height of a skyscraper by less than the width of a paper sheet. And its sunshield must remain perfectly stretched, and its orbit must stay stable to within a few kilometers, even while traveling at tens of thousands of kilometers per hour around the sun. And communication with Earth is handled through NASA's Deep Space Network, which sends commands and receives data across vast distances. And every day the telescope sends back terabytes of information, including high-resolution images and spectral data. And teams of scientists around the world then analyze this data using it to make new discoveries and refine our understanding of the universe. And Webb's mission goals extend far beyond its first few years, as it was designed to operate for at least a decade, though its fuel supply could allow it to continue working for much longer. And over time, it will study everything from the icy moons of our solar system to the faint glow left over from the Big Bang, and it may even help solve mysteries that we have not yet imagined. And the success of the telescope's design was the result of international collaboration, with NASA working alongside the European Space Agency and the Canadian Space Agency, combining resources, expertise, and technology from across the world, and each partner contributed vital components, as the European agency provided the launch and part of the spectrograph, while the Canadian agency built the fine guidance system. And this teamwork reflects the shared human desire to explore the unknown and expand our understanding of existence. In every part of the telescope structure was built with precision and purpose, as the main body or spacecraft bus holds the electronics, communication systems, and propulsion units, and it is what keeps the observatory powered, cooled, and pointed in the right direction. And the telescope's instruments are mounted on an integrated science module, which connects directly to the mirrors, and together these parts form a delicate balance of strength and lightness, as the entire structure weighs only about 6.5 tons, remarkably little considering its enormous size and complexity. And keeping the telescope at the right temperature is one of its greatest challenges, as the difference between the hot and cold sides of the sun shield is so extreme that it could cause thermal stress or distortions if not carefully managed, and engineers had to design materials that could survive such conditions for years without shrinking, stretching, or tearing. And the layers of the sun shield are tensioned by a network of cables and pulleys, keeping them perfectly spaced so that heat cannot pass through. And the observatory's pointing system is equally impressive, as to capture sharp images of distant galaxies, Webb must remain steady to within a fraction of an arc-second, roughly the width of a human hair seen from a kilometer away. And this precision is achieved using reaction wheels, gyroscopes, and sensors that constantly adjust the telescope's orientation. And even the smallest vibrations must be controlled, and the fine guidance sensor ensures that the telescope locks onto its targets with unwavering stability. And when people see the dazzling images Webb produces, it can be easy to forget the incredible amount of science and engineering behind each one, as every photograph represents countless calculations, alignments, and data corrections. And the colors we see are not what the telescope sees directly, but are created by translating infrared light. For thousands of years, humanity lived inside a beautiful lie, a cosmic fairy tale so convincing that even the smartest minds on Earth never questioned it. The belief that our solar system was not just enormous, but literally everything. The entire universe wrapped around us like a comfortable blanket. And this illusion began with the ancient Babylonians, who mapped the night sky 4,000 years ago, watching the planets wander between the stars, and assuming these lights were gods moving across a heavenly dome that existed solely for human observation. And this geocentric model, the Earth-centered universe, dominated human thought for centuries, with ancient astronomers like Ptolemy building entire mathematical systems around the idea that Earth sat motionless at the center of creation, while crystal spheres carried the planets and stars around it in perfect circles. And to early observers, the cosmos appeared vast and majestic, yet in their minds, it all existed for humanity's sake. The stars were seen as distant decorations, lights attached to the edge of a heavenly ceiling, and it wasn't arrogance as much as ignorance. Humanity simply lacked the tools to see farther, or the means to question the illusion of size that the night sky presented. And for the ancients, the visible sky was the limit of existence. The sun, the brightest and most dominant object, seemed vast and powerful, but even it was thought to be just one part of a universe designed around Earth. And the distances between the planets appeared immense, but only because people had no real sense of measurement beyond what their eyes could see. And the idea of distance in space was abstract, something guessed at, but never understood. And this illusion began to shift slowly during the Renaissance, a period of awakening that started in the 14th century and transformed how people saw the world. And in the early 16th century, a Polish mathematician named Nicolaus Copernicus proposed something radical, that the sun, not the Earth, was at the center of the universe. His model placed Earth and the other planets in orbit around the sun, an idea that completely shattered centuries of belief. Yet even Copernicus underestimated the true scale of the solar system. He knew the planets were far apart, but had no way of knowing just how far. To him and his followers, the sun still seemed close, the planets just beyond reach, and the stars still distant, but part of the same grand structure. And the idea that space could extend infinitely was almost too vast to accept. And a few decades later, Galileo Galilei pointed a simple telescope at the sky and changed everything again. In the year 1610, he observed 4 small moons orbiting Jupiter, which proved that not everything revolved around Earth. He also saw that Venus went through phases just like the moon, showing that it must circle the sun, and the illusion of a small Earth-centered universe began to crumble. Yet even as Galileo's discoveries opened new horizons, the solar system still appeared enormous to the human mind. It was the known edge of existence, a grand clockwork of celestial bodies, moving in harmony with the sun shining at its heart, and beyond the planets lay only mystery and speculation. Some thinkers believed the stars were other suns, perhaps even with their own planets, but there was no way to prove it, and the solar system seemed vast, but it was still seen as the central masterpiece of creation. And in the 17th century, Johannes Kepler calculated that planets moved not in perfect circles as once believed, but in ellipses. His laws of planetary motion allowed scientists to predict the movements of the planets with remarkable accuracy. Then Isaac Newton, in the late 17th century, explained gravity, the invisible force that held the planets in their orbits. These discoveries deepened humanity's understanding of the solar system's mechanics, but not yet its scale, and the distances between the planets were measured in terms of astronomical units, the distance from Earth to the sun. But even this was difficult to grasp. The numbers were so large that they meant little to ordinary people, and to most the solar system remained an unfathomable expanse, an enormous cosmic sea that humanity could never cross. And by the 18th and 19th centuries, astronomers had discovered Uranus and Neptune, expanding the boundaries of the known solar system. And William Herschel, who discovered Uranus in 1781, believed he had reached the edge of creation itself. The planet seemed to stretch endlessly outward from the sun, forming a vast family of worlds, and the idea of the solar system as the ultimate frontier became deeply rooted in the imagination. Artists, poets, and scientists alike described it as an enormous celestial empire, ruled by the sun, with each planet a kingdom of its own. And to think that there might be more beyond was almost heretical. Humanity was still trapped in a comforting illusion, the belief that their cosmic neighborhood was the entire universe, and even the discovery of comets and asteroids did little to change this perception. When telescopes became more powerful in the 19th century, they revealed countless smaller bodies orbiting between Mars and Jupiter, forming what came to be known as the asteroid belt. And to many, it seemed that the solar system was filled with endless objects, stretching farther than anyone could imagine, and the distances between planets were described in millions and billions of miles. But such numbers were so large that they lost all meaning. And to the human mind, the solar system was a vast, almost infinite realm, the ultimate measure of cosmic scale. And people imagined the edge of the solar system as a dark frozen boundary where the sun's light faded into the void, beyond which nothing existed. Then, in the early 20th century, the illusion began to weaken once more. Telescopes grew stronger, and astronomers started to suspect that the stars were not just part of our solar system, but distant suns, each with its own possible worlds. And in the 1920s, Edwin Hubble made a discovery that forever shattered humanity's understanding of size. Using the 100-inch Hooker telescope at Mount Wilson Observatory, he found that the Andromeda Nebula was not a cloud of gas within our galaxy as once thought, but a completely separate galaxy, one of countless others. And this revelation transformed the solar system from being the center of creation to being merely one small corner of an unimaginably vast universe. And the illusion of size that had lasted for millennia was finally broken. Yet many still found comfort in the familiar grandeur of the solar system. Even so, the sense of distance within our own cosmic neighborhood continued to inspire awe. The sun was nearly 150 million kilometers from Earth, a figure that seemed unthinkably large, and the outer planets were so far away that even light traveling at nearly 300,000 kilometers per second took hours to reach them. And when astronomers spoke of these numbers, they felt almost poetic. The solar system still appeared enormous compared to human experience. But now it was understood to be only a tiny part of something far greater. In the mid-20th century brought another turning point. For the first time, humanity began to send machines beyond Earth's atmosphere. In the year 1957, the Soviet Union launched Sputnik, the first artificial satellite, and only a few years later, Yuri Gagarin became the first human to orbit Earth. And these milestones marked the beginning of space exploration, and soon after humanity turned its gaze outward toward the moon, the planets, and the far reaches of the solar system, and the illusion of size began to transform once again, this time through direct exploration rather than theory. And in the 1960s and 70s, robotic probes ventured to the nearby planets. The Mariner missions sent back the first close-up images of Venus and Mars, revealing worlds that were not distant mysteries, but solid places, barren, rocky, and real. And when the Apollo missions landed humans on the moon in 1969, the solar system suddenly felt smaller. For the first time, people saw Earth from space, a fragile blue sphere floating in darkness, and the vastness that had once seemed endless was now something humanity could measure and explore. Yet even as the solar system grew more familiar, it still felt huge. The outer planets, Jupiter, Saturn, Uranus, and Neptune, remained far beyond the reach of human travel, and the sun's outer domain was still wrapped in mystery, and the illusion of the solar system's size reached its greatest test in the late 20th century with the launch of the Voyager probes. In the year 1977, NASA sent two spacecraft, Voyager 1 and Voyager 2, on grand journeys to explore the outer planets, and these missions changed human understanding of space forever. Over the years, the Voyagers sent back breathtaking images of Jupiter's swirling storms, Saturn's shimmering rings, Uranus's tilted atmosphere, and Neptune's deep blue winds. And each planet, once thought to be just points of light, was revealed in stunning detail, and the solar system no longer seemed like an abstract diagram in a textbook. It became a living, dynamic place. And as the Voyagers continued their journeys beyond Neptune, they entered a region known as the Kuiper Belt, a vast field of icy bodies and dwarf planets. And beyond that lay the mysterious Oort cloud, a hypothetical shell of comets stretching nearly 2 light-years from the sun. And even at these extreme distances, the sun's gravity still held sway. And Voyager 1 eventually crossed the boundary known as the heliopause, entering interstellar space. For the first time, a human-made object had left the solar system. Yet in the grand scale of the cosmos, it had barely moved at all. And the probe, traveling at nearly 60,000 kilometers per hour, would take tens of thousands of years just to reach the nearest star. And what once seemed enormous, the solar system, was now just a tiny bubble in an endless ocean of space, and this realization was both humbling and astonishing. For most of human history, the solar system had represented the ultimate boundary of existence. Early astronomers had gazed upward and believed they were looking at the whole of creation. Even as telescopes revealed more detail, the scale of the solar system still seemed vast beyond comprehension. But as science advanced, and as spacecraft, like Voyager, ventured farther and farther away, the truth became undeniable. The solar system was not the universe's center, nor even a large part of it. It was merely a small family of planets, orbiting an ordinary star among billions of others. And the illusion of size had been built not on arrogance, but on perspective. Human senses are limited to what the eyes can see, and the mind can imagine. And when people first measured distance by walking across the land or sailing across the sea, even the moon seemed impossibly far away, and the early astronomers could not have imagined distances measured in millions or billions of kilometers. To them, the heavens were vast, because their world was small. And as tools improved from simple telescopes to giant observatories, and finally to space probes, that perspective widened, and what once seemed enormous began to shrink. And the transformation of this perception can be traced through humanity's changing relationship with scale. In the 17th century, a telescope that magnified the moon made people feel as though they had touched another world. In the 20th century, photographs taken by robotic explorers made the outer planets seem almost close, and in the 21st century, space observatories like Hubble and James Webb have peered beyond the solar system entirely, capturing light from galaxies that formed billions of years ago. And each step has revealed that our solar system, while wondrous and complex, is a mere speck in a cosmic web that stretches across unimaginable distances. And still, for the people of earlier times, the illusion of size was powerful. It shaped myths, religions, and philosophies. The planets were gods, the stars were eternal fires, and the sun was the life-giving heart of the universe. And the solar system was not only vast, it was sacred. To suggest otherwise was to challenge the very order of creation. And when Copernicus, Galileo, and Kepler presented their findings, they were not only changing science, they were reshaping humanity's place in the cosmos, and the solar system became a stage for discovery rather than divine perfection. But its immensity remained awe-inspiring. Even as humanity's knowledge grew, the feeling of vastness never fully faded, and the distances within the solar system are still immense compared to human experience. It takes light more than 8 minutes to travel from the sun to Earth. It takes over 5 hours to reach Pluto, the small icy world that marks the outer edge of the main planetary system. And a spacecraft traveling at tens of thousands of kilometers per hour takes years just to move between neighboring planets. And the illusion of size may have been replaced by understanding, but the sense of wonder remains. And the Voyager probes, now drifting through the interstellar medium, continue to send faint signals back to Earth, whispers from the edge of the sun's influence. They remind humanity of how far it has come and how small it still is, and the once vast solar system is now just a pinpoint of light within the Milky Way galaxy, which itself is one among hundreds of billions of galaxies in the observable universe. Yet for early astronomers who had no concept of galaxies or cosmic scale, the solar system's grandeur was enough to fill the imagination, and this long journey from the early star watchers of ancient Babylon to the deep space travelers of the modern era reveals more than scientific progress. It shows the evolution of human humility. Each discovery that made the universe larger also made humanity smaller. Once people thought Earth was the center of all things. Then they learned that it was only one planet among many. Later they discovered that the sun was just one star among countless others. Finally, they began to see that even the galaxy itself was not unique, and the illusion of size was not destroyed in a single moment, but peeled away layer by layer, replaced by a deeper understanding of reality. And yet the illusion still has power. When people look at images of Saturn's rings or Jupiter's storms, the mind struggles to grasp their true scale. Saturn's rings stretch hundreds of thousands of kilometers wide, but they are so thin that they would fit easily between clouds on Earth. Jupiter's Great Red Spot, a storm larger than our entire planet, rages continuously as though it were eternal. And these facts are both real and surreal, showing that even within the solar system's relatively small scale, in cosmic terms, there is still an immensity beyond ordinary imagination. And from the first moment, an ancient observer marked the motion of Venus, to the time when Voyager 1 crossed into interstellar space, the human sense of scale has expanded 1,000-fold, and what was once seen as the universe is now known to be a small neighborhood of cosmic space. But in that smallness lies a profound truth, that humanity's ability to perceive and explore has grown far beyond its physical limits. Then the illusion of size may have been an error, but it was also a necessary step in the path of understanding. Without it, there might have been no reason to reach beyond the stars, no desire to discover what lies beyond. And the story of how humanity once believed the solar system to be vast and central is also the story of how curiosity overcame illusion. And every telescope built, every calculation made, and every probe launched has brought the universe into sharper focus, revealing both its enormity and our own smallness within it. And the early astronomers, limited by what they could see, created a cosmos centered around humanity. And the explorers of later centuries replaced that illusion with knowledge, a knowledge that continues to grow as new generations push further into the unknown. And even now, as telescopes peer into galaxies, billions of light years away, the solar system retains its sense of wonder. It remains the cradle of life, the place where consciousness first opened its eyes to the stars. It may no longer seem enormous in comparison to the vastness of the universe, but to humanity, it will always be the first great ocean crossed by the ships of discovery. And the illusion of size that once made the solar system seem infinite has faded, replaced by a more profound realization that the true vastness of the universe lies not just in distance, but in the endless reach of human curiosity. On Valentine's Day, in the year 1990, a machine that humanity had launched 13 years earlier did something no camera had ever done before. It turned around and looked back at home from a distance, so vast that the numbers themselves feel like a form of poetry. Voyager 1 was 6 billion kilometers away, 3.7 billion miles, 40.5 astronomical units from the Sun, traveling at 60,000 kilometers per hour, so far out that it takes light 5.5 hours to cross the gap between Earth and the spacecraft. And from that impossible distance, it captured an image that would break something fundamental in the human psyche. A photograph that shows our entire world, every mountain, every ocean, every city, every person who has ever lived, every war, every love story, every moment of joy and suffering, reduced to a single pixel, a pale blue dot floating in a scattered beam of sunlight. And this was not an accident. It was a deliberate choice made by the Voyager imaging team, led by the astronomer Carl Sagan, who had first proposed the idea 9 years earlier, in 1981, arguing that humanity needed to see its home from this impossible perspective, not for scientific data, but for something deeper, a visual proof of our cosmic insignificance. And so on February 13th, 1990, Voyager 1 powered up its cameras, which had been dormant for years, taking 3 hours to warm them from the deep cold of space. And then it began a carefully choreographed sequence, snapping 60 frames that would become the first and only family portrait of our solar system, capturing Neptune, Uranus, Saturn, Jupiter, Venus, and finally Earth, though Mercury was too close to the Sun to be imaged, and Mars was blocked by scattered light bouncing inside the camera optics. And when the spacecraft turned its narrow-angle camera toward Earth, it had to point within 3 degrees of the Sun, a dangerous maneuver that risked damaging the sensors with direct sunlight. But the angle was perfect. catching Earth as a crescent, 0.12 pixels wide, a tiny speck of blue suspended in a sunbeam created by camera artifacts, light scattering inside the optics, a happy accident that made our world appear even more fragile and alone. And the image data took months to reach Earth, transmitted at a painfully slow rate across the vast distance, arriving in pieces through NASA's Deep Space Network, with the final, complete image not assembled until May 1st, 1990. And when Carl Sagan first saw it, he understood immediately what it meant, writing later that this point of light is where we live, where everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives, and the aggregation of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. And this was the first time humanity had truly seen itself from outside, not as the center of creation, but as a speck of dust. And the emotional impact of this image cannot be overstated. It was simultaneously the most humbling and the most unifying photograph ever taken, showing that all our divisions, all our borders, all our wars and conflicts happen on a fraction of a pixel in a vast cosmic image. And the technical achievement behind this photograph was itself remarkable. Voyager 1 was launched in 1977, designed for a 4-year mission to study Jupiter and Saturn, but it kept working, flying past Uranus and Neptune, and then continuing into the void, becoming the first human-made object to enter interstellar space in 2012. And its cameras were never meant to operate at such distances. The imaging system used Vidicon tubes, old technology even by 1970s standards, and the spacecraft's computer had only 69 kilobytes of memory, less than a single modern digital photograph, and yet it captured this profound image using a narrow-angle camera with a focal length of 1,500 millimeters, an aperture of 50s, and a field of view so small that finding Earth was like aiming a rifle at a moving target from 3.7 billion miles away, and the exposure time was just 0.05 of a second. Yet it captured enough photons bouncing off Earth's oceans and clouds to create that pale blue dot. And the color is significant. The blue comes from Rayleigh, scattering in our atmosphere, the same phenomenon that makes the sky blue, and from the oceans that cover 71% of our planet's surface. And the paleness comes from the distance, the faintness, the way Earth fades into the background of space. And this image changed everything. It became the cover of Carl Sagan's book, Pale Blue Dot, published in 1994, and it has been reproduced countless times, referenced in speeches, hung in classrooms, tattooed on skin. It is perhaps the most important photograph ever taken, not for what it shows, but for what it means. And it arrived at a perfect moment, just as the Cold War was ending, as humanity was beginning to think globally about environmentalism, about climate change, about our shared responsibility for this fragile world. And the image gave visual form to these ideas, showing Earth not as a vast planet, but as a vulnerable island in an ocean of emptiness. And the Voyager mission itself was a miracle of engineering. 2 spacecraft, launched 16 days apart in 1977, taking advantage of a rare planetary alignment that occurs once every 175 years, using gravity assists to slingshot from Jupiter to Saturn, to Uranus to Neptune. And Voyager 1's trajectory was designed to fly close to Titan, Saturn's largest moon, which bent its path out of the plane of the solar system, sending it on a journey that would eventually take it beyond the heliosphere, the bubble of solar wind that surrounds our sun. and after the Neptune flyby in 1989, the Voyager team knew the spacecraft would soon run out of power, its radioactive thermoelectric generators producing less and less electricity each year. And so Carl Sagan's proposal to take one last look home was approved, a final gift, before the cameras were powered down forever, and the timing was critical. Voyager 1 was moving at such speed that the window to capture all the planets in a single mosaic was narrow, and the spacecraft's orientation had to be precise, using its gyroscopes and thrusters to point the camera platform with incredible accuracy, and the data rate was painfully slow. Only 160 bits per second, meaning each image took minutes to transmit, and the Deep Space Network had to listen carefully, picking up the faint signal from the edge of the solar system. A whisper from a machine that had traveled farther than anything built by human hands. And when the pale blue dot image was finally processed and released, the world reacted with awe. Newspapers ran it on front pages. Television news programs discussed it for days, and Carl Sagan's poetic description of it on television, his voice cracking with emotion as he described our world, a lonely speck in the great enveloping cosmic dark, resonated with millions. And the image has only grown more powerful with time, as we have discovered thousands of exoplanets, as we have seen deeper into the universe with Hubble. And now Webb, the pale blue dot, remains the most personal image of cosmic perspective because it is us. It is our home. It is the only place in the entire universe where we know life exists. And seeing it from so far away, reduced to a single pixel, puts everything in context. All our problems, all our achievements, all our history, contained in that tiny blue point of light, and the scientific community has continued to celebrate this image. NASA released the updated version in 2020, processing the original data with modern techniques to reduce noise and enhance the color, showing Earth as slightly less pale, slightly more blue, but still just as small, just as alone. And the Voyager spacecraft continue to send data back, even now, more than 45 years after launch, from beyond the heliopause, measuring the density of interstellar plasma, sending back readings that take 22 hours to reach Earth at the speed of light. And they carry the golden record, a message to any future finders, containing sounds and images of Earth, including Chuck Berry's Johnny B. Good, greetings in 55 languages, the brainwaves of Andruyan, and the location of our sun relative to 14 pulsars, a cosmic map that might one day be found by another civilization. And the pale blue dot image is perhaps the most important message on that record, a visual proof that we existed, that we looked at ourselves from the edge of the solar system and understood what we were seeing. And this image set the stage for everything that came after. It prepared humanity for the even deeper perspective that Webb would provide. Because if seeing Earth as a pale blue dot from 6 billion kilometers away was shocking, seeing thousands of galaxies in a patch of sky smaller than a grain of sand would be incomprehensible. And yet both images share the same message, that we are small, that we are fragile, that we are part of something infinitely larger than ourselves. And the pale blue dot taught us humility, but it also taught us unity, showing that all of us, everyone who has ever lived, everyone who will ever live, shares this tiny point of light. And the image has been used in countless ways, in environmental campaigns, in peace movements, in classrooms, where children learn about the solar system. It is a reminder that we are all in this together, that our differences are meaningless on a cosmic scale, that we are the crew of a single spaceship, Earth, traveling through the void. And the Voyager mission managers, who made the decision to take this image, who warmed up the cameras and pointed them back toward home, knew they were making history. They understood that this would be the last image Voyager 1 would ever take, that after this, the cameras would be powered down forever to conserve electricity for the remaining instruments. And they chose to use some of the spacecraft's final power to show us ourselves. A decision that has been vindicated 1,000 times over, because no other image has had such a profound effect on human consciousness, and the technical specifications of the photograph are almost as mind-bending as the image itself. Voyager 1's narrow-angle camera had a resolution of 800 by 800 pixels, and Earth occupies less than a single pixel in that frame, meaning that our entire planet, with its 7.8 billion people, its 510 million square kilometers of surface area, its towering mountains and deep oceans, all of it fits into less than 1/800th of the image width. And the camera used a blue filter to capture this particular frame, which is why Earth appears as a pale blue dot rather than a white or brown one. And the scattered light rays that frame our planet are not real sunbeams, but artifacts of the camera's optics, light bouncing around inside the lens assembly. Yet they create the perfect visual metaphor, making Earth look like a tiny mote caught in a shaft of light. And this accident of optics became the most powerful part of the image. And Carl Sagan's words about the photograph have become as famous as the image itself. His description of Earth as a mote of dust suspended in a sunbeam, his reminder that every saint and sinner, every king and peasant, every creator and destroyer of civilization lived on that dot, and his warning that our planet is a lonely speck in the great enveloping cosmic dark, that there is nowhere else, at least in the near future, to which our species could migrate, that we must cherish and preserve our pale blue dot, because it is the only home we have ever known. And these words have been quoted by presidents, printed on posters, shared across the internet millions of times, just because they capture perfectly what the image makes us feel. A mixture of awe and responsibility, of humility and love for our fragile world. And the pale blue dot image has influenced everything that came after. It made the concept of Earth as a single interconnected system visceral and real. It gave visual proof to the idea that we are all in this together, and it prepared humanity for the even greater cosmic perspective that would come with Hubble's deep field images, and now Webb's infrared vision, because each step deeper into space shows us the same truth from a different angle, that we are small, that we are precious, that we are connected to everything. And the Voyager spacecraft that took this image are still out there, still sending back data, having crossed the heliopause in 2012, entering true interstellar space, where the solar wind no longer protects them from the harsh radiation of the galaxy. And they carry with them the golden record, a time capsule of humanity, and perhaps one day, in 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445, and maybe someone or something will find it and see the images we included, and understand that we once looked at ourselves from the edge of our solar system and saw a pale blue dot, and perhaps they will look at their own world the same way, and understand what we understood, that we are all together on this tiny speck of dust, and that knowledge changes everything. And this is why the pale blue dot remains the most important photograph ever taken, because it was the first time we saw ourselves truly from the outside, the first time we understood our cosmic loneliness and our planetary unity, and it set the stage for Webb's discoveries. Because if one pixel could contain all of human history, then what does it mean when Webb shows us thousands of galaxies in a patch of sky, smaller than a grain of sand, each galaxy containing billions of stars, each star perhaps with planets, each planet perhaps with life? And this is the progression of cosmic perspective, from thinking we were the center of everything, to seeing ourselves as a pale blue dot, to now understanding that we are one dot among billions. And yet that dot is special, because it is the only place we know where the universe has become conscious of itself. And the pale blue dot image will continue to inspire, to humble, to unite, as long as humanity looks at it and remembers what it shows us, that we are all crew members on the same tiny spaceship, that our differences are meaningless in the cosmic scale, and that we have a responsibility to cherish and protect this fragile world. Because for now, it is the only home we have and the Voyager team who made this possible, who warmed up those cameras and pointed them back toward home, who waited months for the data to trickle back across the void, who processed the images and saw Earth as a single pixel. They gave us a gift that will last as long as our species endures, a reminder of who we are and where we stand in the universe. And every time we look at that image, every time we see that pale blue dot suspended in a sunbeam, we should remember that everything we care about, everything we fight for, everything we love, is right there on that mote of dust, and that knowledge should change how we treat each other and how we treat our world, because we are all together on this tiny speck of dust in the cosmic dark, and there is no backup plan, no other pale blue dot waiting for us if we ruin this one. And this is the message that Voyager 1 sent back from the edge of the solar system, a message that took 5.5 hours to cross the void at the speed of light, a message that said, look at yourselves, see how small you are, see how precious you are, and act accordingly. And this image, this single pixel containing everything we have ever known, is the foundation upon which Webb's deeper perspective is built. Because if the pale blue dot taught us humility, Webb teaches us that even in our smallness, we are connected to everything, that the atoms in our bodies were forged in stars that died in galaxies. Webb can see that we are not just observers of the cosmos, but products of it. And this is the next step in understanding our place in the universe, moving from seeing ourselves as a dot to seeing ourselves as part of the infinite web of creation. And the pale blue dot was the first step on that journey, the first time we truly saw ourselves from the outside. And it remains the most powerful image ever captured because it contains everything, everyone, every story, every hope, every dream, every tragedy, every triumph, all in a single pixel, a pale blue dot suspended in a sunbeam, looking lonely and precious and impossibly small against the vast enveloping cosmic dark. When the James Webb Space Telescope opened its golden eye for the first time in July 2022, pointed it at a patch of sky no larger than a grain of sand held at arm's length, it captured an image that rewrote the entire story of cosmic scale, revealing not dozens or hundreds, but thousands upon thousands of individual galaxies, crowded into a space so tiny that it represents less than 1/10,000,000th of the total sky. And this first deep field image, officially named SMACS 0723, shows a massive galaxy cluster, located 4.6 billion light-years away, that acts as a natural cosmic magnifying glass, its immense gravity bending and warping space-time itself to create gravitational lensing effects that amplify the light from galaxies behind it, some of which are so distant that their light has traveled for over 13 billion years to reach Webb's mirrors, meaning we are seeing these galaxies not as they are today, but as they were when the universe was less than 4% of its current age, a time when the first stars were just beginning to ignite, and the cosmic dawn was breaking over a universe that had been dark for hundreds of millions of years. And within this single image, Webb identified galaxies that are 100 times fainter than anything Hubble could detect, revealing structures that push at the very limits of our understanding, including massive galaxies that appear far too developed for their age, suggesting that star formation and galaxy assembly happened much faster in the early universe than any theoretical models had predicted. And these galaxies show spiral arms, disk structures, and organized shapes that should not exist so soon after the Big Bang, forcing astronomers to reconsider fundamental assumptions about how quickly matter could collapse under gravity to form the building blocks of cosmic structure and beyond the galaxies themselves. Webb's infrared vision penetrates the veils of cosmic dust that have hidden star formation from all previous telescopes, revealing the pillars of creation in the Eagle Nebula, not as static columns of gas, but as dynamic cauldrons where new stars are actively being born, their intense radiation boiling away the surrounding material, while jets of ionized gas shoot outward at supersonic speeds, and in the Orion Nebula Web, captured protoplanetary disks, the birthplaces of planets, showing detailed rings and gaps where infant worlds are sweeping up dust and gas. And these observations confirm that planet formation is not a rare event, but a natural consequence of star birth, happening everywhere we look. And Webb spectrographs have analyzed the atmospheres of exoplanets with unprecedented detail, detecting carbon dioxide in the thick clouds of WSP-39b, a hot Jupiter located 700 light-years away, finding water vapor in the atmosphere of WSP-96b, and identifying sulfur dioxide, a molecule created through photochemical reactions, proving that complex atmospheric chemistry exists on worlds far beyond our solar system. And in perhaps its most profound discovery, Webb detected carbon dioxide in the atmosphere of a rocky exoplanet for the first time, finding it in the atmosphere of LHS 475b, a planet 41 light-years away that is almost exactly the same size as Earth, though orbiting so close to its star that its surface temperature would melt rock. And this detection proves that Webb can analyze the atmospheres of potentially habitable worlds, opening the door to finding biosignatures, chemical fingerprints of life. In the coming years, and Webb has also identified the earliest complex organic molecules ever found, detecting polycyclic aromatic hydrocarbons in a galaxy 12 billion light-years away, in a galaxy that formed when the universe was only 1.5 billion years old, less than 10% of its current age. And these carbon-rich molecules are the building blocks of life, suggesting that the ingredients for biology were present in the universe far earlier than anyone imagined. And in the same distant galaxy, Webb found water ice, carbon monoxide, and other molecules essential for life, showing that the chemistry of life is not unique to Earth, but is woven into the fabric of the cosmos from the earliest times. And Webb's observations of dying stars have revealed Wolf-Rayet stars in unprecedented detail, capturing star WD 124, 15,000 light-years away, as it sheds its outer layers in powerful stellar winds, creating beautiful nebulae that will one day seed the galaxy with heavy elements. And these observations show how the universe recycles matter, how stars live and die, and spread their ashes across space to form new stars, new planets, and perhaps new life. And Webb has also studied our own solar system with fresh eyes, capturing Jupiter's auroras glowing in infrared light, mapping the temperature variations in its great red spot, a storm larger than Earth that has raged for centuries, and observing the faint rings of Jupiter that are normally invisible to telescopes. And it has studied Saturn's moon Titan, detecting clouds of methane and ethane, mapping its surface features through the thick, hazy atmosphere, and confirming that this moon has weather patterns and liquid cycles similar to Earth, but using hydrocarbons instead of water. And Webb has looked at Mars, analyzing its atmosphere to measure carbon dioxide, water vapor, and dust storms, and it has observed the icy moons of Uranus and Neptune, revealing details that Voyager could not see with its older technology. And perhaps most surprisingly, Webb has discovered new objects in our own cosmic backyard, finding previously unknown asteroids in the main asteroid belt between Mars and Jupiter, and detecting comets entering the inner solar system, showing that even in our own neighborhood, there is still much to discover. And the sheer volume of data is overwhelming, with Webb producing 10 terabytes of raw data every day, images and spectra that are downloaded through NASA's Deep Space Network and processed by teams of scientists around the world. And each image contains thousands of galaxies, each galaxy billions of stars, and around each star perhaps multiple planets. And the statistical implications are staggering. If there are 2 trillion galaxies in the observable universe, and each galaxy contains an average of 100 billion stars, then there are 200 sextillion stars in the cosmos. And if even a tiny fraction of those stars have planets in the habitable zone, the number of potentially life-bearing worlds could be in the billions or trillions. And Webb is giving us the tools to begin answering this question, to move from speculation to measurement, from wondering to knowing. And the telescope has already identified several candidate galaxies that may be members of the first generation of stars, population 3 stars, that are theorized to be massive, hot, and composed only of hydrogen and helium, the pristine material from the Big Bang. And while Webb has not yet definitively proven their existence, it has found galaxies so early in cosmic history that they must contain these first stars, and the spectra show unusual features that suggest the presence of stars unlike any we see today. Stars that would have burned brilliantly and died quickly, exploding as supernovae and seeding the universe with the first heavy elements, the carbon in our bodies, the oxygen we breathe, the iron in our blood, all forged in these ancient stellar furnaces. Webb's observations of the cosmic web, the large-scale structure of the universe, show how galaxies are not randomly distributed, but are arranged in filaments and sheets, with vast voids between them, creating a foam-like structure that spans billions of light years. And by mapping these structures, Webb is helping scientists understand the nature of dark matter and dark energy, the mysterious components that make up 95% of the universe, but which we cannot see directly. And the gravitational lensing effects that Webb observes allow astronomers to measure the distribution of dark matter around galaxy clusters, showing that there is 5 times more dark matter than normal matter, and that it forms halos around galaxies, holding them together with its gravity. And the expansion of space itself, driven by dark energy, is causing these galaxies to recede from us at ever-increasing speeds. And Webb's measurements of distant supernovae and galaxy redshifts are helping to refine our understanding of this acceleration, which will determine the ultimate fate of the universe. And all of these discoveries flow from that first deep field image, which was just the beginning, a 12.5-hour exposure that revealed 25,000 galaxies. And since then, Webb has taken longer exposures, deeper fields, and each time it finds more galaxies, fainter and more distant, pushing back the frontier of the observable universe. And the telescope is designed to operate for at least 10 years, though its fuel supply could allow it to continue for 20 years or more, meaning we are at the beginning of a golden age of discovery, where every week brings new revelations about the cosmos, new questions that challenge our understanding, and new answers that rewrite textbooks. And what Webb has actually seen in the darkness is not just galaxies and stars and planets, but the story of the universe itself, written in light that has traveled across billions of years to reach us. And we are finally able to read that story, to understand our origins, and to see our place in the cosmic drama. And the darkness is not empty. It is filled with structure, with life-giving chemistry, with the echoes of the Big Bang, and with the promise that we are not alone in our ability to look up and wonder, because somewhere out there, in one of those thousands of galaxies, perhaps another pale blue dot is looking back at us, seeing our galaxy as a faint smudge in their deep field image, and asking the same questions we ask. And this is what Webb has given us, a mirror that shows not just the universe, but ourselves, reflected in its infinite depths. The mathematics begin with a number so large, it ceases to function as a number and becomes a form of poetry. 2 trillion galaxies in the observable universe, each containing an average of 100 billion stars, which means there are 200 sextillion stars, a figure that breaks the brain's ability to comprehend scale. And if even 1% of those stars have planets in the habitable zone, that leaves 2 sextillion potential homes for life. And if only 0.1% of those planets develop life, that is still 2 quintillion worlds where biology might exist. And if only 1/1,000,000th of those develop intelligent civilizations, that would be 2 trillion alien species, looking up at their own night skies, wondering if they are alone, and yet we have no evidence of any of them, which is perhaps the most terrifying number of all, the zero in the equation of contact, the silence that screams across the void. And these galaxies are not close together. They are separated by distances that make the word vast feel like a pathetic understatement. The nearest major galaxy to our own Milky Way, Andromeda, is 2.5 million light-years away, meaning the light we see from it tonight began its journey when our ancestors were still learning to use stone tools. And the farthest galaxies Webb can see are over 13 billion light-years distant, their light having traveled for most of the age of the universe. And because space itself has been expanding during that time, those galaxies are now actually 46 billion light-years away, placing them beyond the cosmic horizon, forever unreachable, forever unknowable. And the speed of this expansion is itself a number that defies intuition. The Hubble constant measures approximately 70 kilometers per second per megaparsec, which means that for every 3.26 million light-years you travel into space, galaxies are moving away from us an additional 70 kilometers per second. And at the edge of the observable universe, this expansion exceeds the speed of light itself, which is not a violation of physics, because it is space that is expanding, not objects moving through space. And this creates a cosmic event horizon beyond which we can never see, a boundary that defines our universe as a finite bubble in an infinite ocean. And our own galaxy, the Milky Way, is 100,000 light-years across, containing between 200 billion and 400 billion stars. And our solar system orbits the galactic center at a speed of 220 kilometers per second, completing one full orbit every 230 million years, a journey we call a cosmic year. And since the formation of Earth 4.5 billion years ago, we have completed perhaps 20 of these orbits, and the Sun itself is moving through space at 20 kilometers per second relative to nearby stars, carrying us on a journey through the galaxy that will eventually bring us close to other star systems. Though the distances are so vast that meaningful encounters take millions of years, and our solar system is not large by cosmic standards. The distance from the Sun to Neptune, the outermost major planet, is 4.5 billion kilometers, which light crosses in 4 hours. And the distance to the Oort cloud, the theoretical shell of comets that marks the true edge of the Sun's gravitational influence, is 2,000 astronomical units, or 300 billion kilometers, which light takes 280 days to cross. And Voyager 1, traveling at 60,000 kilometers per hour, will take 300 years to reach the inner edge of the Oort cloud, and 30,000 years to pass through it, and 40,000 years to come within 1.6 light-years of the star Gliese 445, and 300,000 years to pass within 1 light-year of TYC 3135 221, and in all that time, it will have traveled less than 1% of the distance to the nearest star, Proxima Centauri, which is 4.2 light-years away. And if we wanted to send a spacecraft to Proxima Centauri using current technology, it would take 80,000 years, longer than the entire history of human civilization. And the fastest object ever built by humanity, the Parker Solar Probe, will eventually reach speeds of 700,000 kilometers per hour as it loops close to the Sun. But even at that incredible velocity, it would take 6,300 years to reach Proxima Centauri, and the energy required to accelerate a spacecraft to even a fraction of light speed is staggering. The kinetic energy of a 1 kilogram object moving at 10% of light speed is equivalent to 150 kilotons of TNT. And to accelerate a spacecraft the size of Voyager to that speed would require more energy than humanity has produced in its entire existence. And these numbers are not just large, they are existentially crushing. They reduce human ambition to a mathematical absurdity. And yet, they are the reality within which we exist. And the scale of time is equally devastating. The universe is 13.8 billion years old. Earth is 4.5 billion years old. Life began perhaps 3.8 billion years ago. Complex multicellular life, only 600 million years ago. Dinosaurs ruled for 165 million years, and anatomically modern humans have existed for only 300,000 years, which means we have been here for 0.0002% of Earth's history, and 0.00002% of the universe's history, and recorded civilization spans just 5,000 years, 0.000004% of cosmic time. And if we compress the entire history of the universe into a single calendar year, the Big Bang happens at midnight on January 1st, stars form in March, our solar system forms on September 2nd, life begins on September 21st, dinosaurs appear on December 13th, and disappear on December 26th, and all of human history, from the first cave paintings to the James Webb Telescope, happens in the final minute of December 31st at 11:59 p.m., and the Industrial Revolution happens 2 seconds before midnight, and the internet is invented in the final second, and your entire life spans less than 1/10 of 1 second in this cosmic calendar, and the numbers of atoms are equally incomprehensible. There are 10 to the 80th atoms in the observable universe, a number so large that if you tried to count them at a rate of 1 per second, it would take 10 to the 73rd times the age of the universe to finish. And your own body contains 7 octillion atoms, 7 times 10 to the 27th, arranged in precise patterns that create consciousness. And every one of those atoms was forged in the nuclear furnaces of stars that died billions of years ago. The carbon in your cells was made in stars that lived and died before our sun was born. The iron in your blood was created in supernova explosions that scattered heavy elements across the galaxy. And the calcium in your bones came from stars that lived fast and died young, seeding the cosmos with the building blocks of life. And this means you are literally made of stardust, not metaphorically, but physically. The atoms that make up your body have existed for billions of years and will exist for billions more after you are gone, recycled into new stars, new planets, perhaps new life. And the probability of your existence is itself a mathematical miracle. The chance that the exact sperm and egg that created you met at that exact moment is 1 in 400 trillion, and the chance that your parents met and had children is 1 in 20,000, and the chance that every ancestor in your lineage successfully reproduced, going back to the first life, is essentially 0. And yet here you are, reading these words, a conscious being capable of understanding these numbers, and the Drake equation attempts to quantify the probability of intelligent life elsewhere, estimating that there should be between 1,000 and 100 million civilizations in our galaxy alone. But the Fermi paradox asks why we see no evidence of them, and the Great Filter hypothesis suggests that some barrier prevents civilizations from becoming interstellar, perhaps destroying themselves with technology, perhaps failing to survive climate change, perhaps intelligence is inherently self-destructive. And if the Great Filter is behind us, we are rare and precious, but if it lies ahead of us, we are doomed. And the numbers suggest that even if we survive, the time scales of the universe make contact almost impossible. Civilizations might rise and fall in different epochs, separated by millions of years, like ships passing in the night of cosmic time. And the expansion of the universe ensures that eventually all galaxies beyond our local group will recede beyond our cosmic horizon, disappearing forever. And in 100 billion years, an observer in our galaxy would see only darkness, believing themselves alone in an empty universe. And the numbers of entropy are equally final. The second law of thermodynamics ensures that disorder always increases, and the universe is moving toward heat death, where all energy is evenly distributed, and no work can be done, and this will happen in 10 to the 100th years, a number so large that all the stars will have burned out long before, the last star dying in 10 to the 14th years, and black holes will evaporate through Hawking radiation in 10 to the 67th years, and eventually even protons will decay, and all matter will dissolve into radiation, and the universe will become a cold, dark, empty void. And these numbers are not just large, they are final. They are the mathematics of meaninglessness, the proof that everything we do, everything we build, everything we love will eventually be erased by the relentless arithmetic of cosmic time. And yet within these numbers, within this meaningless vastness, we find meaning, because we are the universe's way of understanding itself. We are consciousness emerging from stardust. We are the cosmos made aware. And the fact that we can comprehend these numbers, that we can write them down and understand what they mean, is itself a miracle, a rebellion against entropy, a temporary organization of matter that has become self-aware. And perhaps that is the point. Perhaps the mathematics of meaninglessness is not meaningless at all. Perhaps it is the canvas on which meaning is painted, the vast darkness that makes the tiny light of consciousness precious. And the numbers tell us we are small, we are temporary, we are insignificant, but they also tell us we are rare, we are conscious, we are capable of love and wonder and discovery. And that might be the most important number of all, the one that counts not galaxies or stars or atoms, but the number of beings who can look up at the night sky and feel awe. And that number is currently 7.8 billion, and it is growing. And every one of those 7.8 billion people carries within them the same stardust, the same cosmic heritage, the same ability to understand these impossible numbers. And that is the mathematics that matters, the mathematics of connection, of shared origin, of shared destiny. And while the universe may be indifferent to our existence, we are not indifferent to it. We care, we explore, we seek to understand. And that seeking is perhaps the most significant thing that has ever happened in the 13.8 billion year history of the cosmos. A species that can measure the universe, that can build machines like Webb to look back in time, that can write down the numbers and feel both the terror and the wonder they inspire. And this is the paradox, that in a universe so vast, it renders us meaningless. We find meaning in the very act of understanding our meaninglessness. And the numbers don't just describe the universe, they describe us. We are the numbers made flesh, the equations given consciousness, the mathematics of stardust that has learned to do mathematics. And perhaps that is the ultimate answer to the question of why the universe is mathematical, because it needed to be mathematical to create beings who could understand that it is mathematical. And we are those beings. We are the universe's mirror, its memory, its meaning. And while the mathematics of cosmic scale tells us we are nothing, the mathematics of consciousness tells us we are everything, at least to ourselves. And that might be enough. It might be more than enough. It might be the entire point, that in a universe of 2 trillion galaxies, on a planet of 7.8 billion people, you are reading these words, understanding these numbers, feeling these emotions, and that single moment of consciousness, that 1 second of awareness, might be the most significant event in your entire personal cosmos, the moment when the mathematics of meaninglessness became the mathematics of meaning, and the numbers stopped being just numbers and became a story. Your story, our story, the story of the universe, understanding itself. And that story is still being written with every observation Webb makes, with every calculation we perform, with every moment of wonder we feel. We add another line to the cosmic equation, and perhaps someday, someone somewhere will look at our numbers and understand that we were here, that we looked up, that we asked questions, and that we found answers in the mathematics of the stars. The atoms in your body are older than the sun, older than Earth, older than the solar system itself. And this is not poetry or metaphor. but literal cosmic fact. Because when you break down the composition of a human body into its fundamental building blocks, you find that 62% of the atoms that make up your physical form are hydrogen, and these hydrogen atoms were born in the first second after the Big Bang, 13.8 billion years ago, when the universe cooled enough for protons to form from quarks, and electrons appeared between a millionth and a trillionth of a second after that initial expansion, making these particles 3 times older than Earth, which formed only 4.5 billion years ago, and nearly 10 billion years older than our Sun, which ignited 4.6 billion years ago. And this means that the hydrogen in the water molecules flowing through your bloodstream right now, in the hydrocarbons that form the membranes of every cell in your body, in the DNA that carries your genetic code, has existed for nearly the entire age of the universe, cycling through gas clouds, stars, planets, and now temporarily assembled into the conscious being that is reading these words. And the remaining 38% of your atoms are heavier elements like oxygen, carbon, nitrogen, calcium, and phosphorus. And these atoms have their own incredible origin story, because they were forged in the nuclear furnaces of stars that lived and died billions of years before our solar system existed. And the oxygen that makes up 65% of your body mass, the oxygen you breathe, the oxygen bound to hydrogen in the water, that is 60% of your mass, was created in the first half of the universe's history, with 3/4 of all oxygen in existence today, formed in the first 3.5 billion years after the Big Bang, when massive stars lived fast and died young, exploding as supernovae and scattering their enriched guts across the cosmos. And the carbon that accounts for nearly 20% of your body mass, the carbon that forms the backbone of every organic molecule, the carbon in the proteins and carbohydrates and lipids that sustain your life, was forged in the cores of stars through the triple alpha process, where 3 helium nuclei fuse to form carbon at temperatures exceeding 100 million degrees Kelvin. And these stars then exploded, sending carbon atoms streaming through space to eventually become part of the molecular cloud that collapsed to form our sun and planets. And the nitrogen in your amino acids, the calcium in your bones, the phosphorus in your DNA, all were created through similar processes, with phosphorus formed in supernovae explosions that reached temperatures of billions of degrees, and calcium produced in the final moments of massive stars before they collapsed. And every one of these atoms has traveled an unimaginable journey to become part of you, starting as hydrogen in the early universe, being fused into heavier elements in stellar cores, being blasted across galaxies by supernova shockwaves, drifting through space for millions or billions of years, becoming part of molecular clouds, collapsing into new star systems, incorporating into planets, cycling through geological processes, entering the biosphere through chemical reactions, becoming part of ancient organisms, passing through countless generations of life, and finally, through an infinite series of improbable events, becoming part of the specific sperm and egg that created you. And this means that the atoms in your right hand likely came from different stars than the atoms in your left hand, because the supernova that seeded one region of space with heavy elements might have been different from the supernova that seeded another region. And the mixing of these atoms in the primordial solar system was not uniform, creating a cosmic heterogeneity. That means you are literally stitched together from the ashes of multiple dead stars. And the James Webb Space Telescope has confirmed this story by observing distant galaxies that existed when the universe was less than 3% of its current age, finding oxygen and carbon in these ancient structures, proving that the elements of life were present in the universe far earlier than anyone imagined. And Webb's spectrographs have detected carbon dioxide, water vapor, and methane in the atmospheres of exoplanets, showing that the chemistry that created life on Earth is not unique, but is woven into the fabric of the cosmos from the earliest times. And the telescope has found polycyclic aromatic hydrocarbons, complex organic molecules, in galaxies 12 billion light-years away, demonstrating that the building blocks of biology were available when the universe was only 1.5 billion years old. And this means that the atoms in your body are not just ancient, but are also universal. They are the same atoms that might be forming life on distant worlds right now. The same carbon, the same oxygen, the same hydrogen, arranged by the same physical laws. And the hydrogen atoms that make up most of your body are the oldest things you will ever touch. Because while protons formed in the first second after the Big Bang, they did not combine with electrons to form neutral hydrogen atoms until about 380,000 years after the Big Bang, when the universe had cooled to 3,000 degrees Kelvin, allowing electrons to settle into orbits around protons without being immediately knocked away by high-energy photons. And this moment, called recombination, is what we see as the cosmic microwave background radiation, the afterglow of the Big Bang. And the hydrogen atoms formed then have existed ever since, passing through the first stars, the first galaxies, the formation of our solar system, and now into you. And the heavier elements have their own timeline, with the first stars forming around 100 million years after the Big Bang, living for only a few million years before exploding as supernovae and spreading their enriched material. And this process repeated for billions of years, with each generation of stars creating heavier elements and enriching the universe, until by the time our solar system formed 4.5 billion years ago, the universe had been processing hydrogen into heavier elements for 9.3 billion years, creating the rich chemical soup from which Earth and life could form. And the specific atoms that make up your body have been part of this cycle for varying lengths of time, with some hydrogen atoms being 13.8 billion years old, some oxygen atoms being 10 billion years old, some carbon atoms being 8 billion years old, and some of the rarer elements like iodine or gold being perhaps only a few billion years old. And this creates an average atomic age for your body that is somewhere around 10 billion years, meaning that you are, on average, twice as old as Earth and nearly 3 times as old as the human species. And this perspective changes everything about how we understand our identity, because we are not just temporary beings who exist for a few decades. We are ancient structures of matter that have been cycling through the universe for billions of years, temporarily organized into a pattern that calls itself human. And this pattern will persist for perhaps a century before the atoms disperse again, returning to the Earth, to the atmosphere, to the oceans, and eventually, when the sun expands and engulfs our planet in 5 billion years, these atoms will be released back into space, perhaps to become part of new stars, new planets, new life, and the cycle will continue. And the James Webb Space Telescope has given us the ability to see this cycle in action, watching as new stars form from the ashes of old ones, observing the chemical enrichment of galaxies over cosmic time, and measuring the abundance of heavy elements in the early universe. And what Webb reveals is that we are not separate from the cosmos, but are the cosmos. We are the universe's way of experiencing itself. The atoms in our bodies have been part of supernova explosions. They have drifted through interstellar clouds. They have been heated to millions of degrees in stellar cores. They have been frozen in comets in the outer solar system. And now they are part of a conscious being who can look up at the night sky and understand what they are seeing. And this is the ultimate form of cosmic recycling, where the universe doesn't just reuse matter, it reuses information. It creates beings who can carry forward the story of creation, who can remember the Big Bang, who can calculate the age of atoms, who can build telescopes to see their own origins. And the hydrogen in your body, the oldest atoms, are also the simplest, just one proton and one electron, and yet they are capable of forming water, the molecule that makes life possible. and they can form organic compounds when combined with carbon and oxygen, and they can store energy in chemical bonds, and they can be split apart in the sun's core through nuclear fusion, releasing the energy that powers life on Earth. And this same process happens in stars across the universe, in galaxies Webb can see, in galaxies so distant that their light has been traveling for 13 billion years. And when we look at those galaxies, we are seeing the same hydrogen, the same processes, the same physics that created us. And the carbon in your body is particularly special because it is the element of complexity. It can form 4 chemical bonds, allowing it to create the infinite variety of organic molecules. And carbon is created in the triple alpha process, where 3 helium nuclei fuse in the cores of stars that are at least 5 times more massive than our sun. And these stars burn through their fuel in just a few million years, then explode as supernovae. And in the final moments of the explosion, temperatures reach billions of degrees, creating even heavier elements and scattering them across space. And the carbon atoms in your body were part of those explosions. They traveled at thousands of kilometers per second through the galaxy. They mixed with interstellar gas. They collapsed into molecular clouds. They became part of the solar nebula. They incorporated into asteroids and comets and planets. And eventually they became part of the first life on Earth. And through billions of years of evolution, they became part of you. And the oxygen in your body, which you need to breathe every moment, was also created in massive stars through the CNO cycle, where carbon, nitrogen, and oxygen catalyze hydrogen fusion. And when these stars exploded, they released oxygen into space. And this oxygen then formed water molecules, which are essential for life as we know it. And the water in your body has been through countless cycles. It has been in oceans, in clouds, in rain, in rivers, in other organisms, and now it is in you. And the nitrogen in your amino acids, the building blocks of proteins, was also forged in stars. And the calcium in your bones, which gives them strength, was created in supernovae. And the phosphorus in your DNA, which stores your genetic information, was also created in stellar explosions. And every element heavier than iron, including the iodine in your thyroid, the copper in your blood, the zinc in your enzymes, the gold in your jewelry, was created in the even more extreme conditions of neutron star mergers, where 2 dead stars collide at a significant fraction of the speed of light, creating temperatures and pressures so extreme that heavy elements are formed through the rapid neutron capture process. And these elements are then flung across the galaxy, eventually finding their way to Earth and into your body. And the fact that we can trace the origin of every atom in our bodies to specific cosmic events, to the Big Bang, to stellar fusion, to supernova explosions, to neutron star collisions, is one of the most profound discoveries of modern astrophysics. And the James Webb Space Telescope is allowing us to see these processes happening in real time, watching as massive stars explode in distant galaxies, observing the chemical signatures of neutron star mergers, and measuring the abundance of heavy elements in the early universe. And what Webb shows us is that the story of our atoms is not unique. It is the universal story of matter in the cosmos. And we are the latest chapter in that story, a chapter written in conscious flesh. And the age of your atoms means that you are not just connected to the cosmos, you are the cosmos. You are ancient hydrogen that has temporarily become self-aware. You are stardust that has learned to do calculus. You are the universe's memory of its own creation. And this perspective should change how you see yourself, because while your consciousness is temporary, the matter that makes up your body is nearly eternal, and the pattern of information that is you will dissipate, but the atoms will continue, and they will become part of new life, new consciousness, new stories, and the cycle will continue for billions of years until the last stars burn out and the universe goes dark, and even then, the atoms will remain, perhaps decaying into radiation over incomprehensible timescales, but always conserving the information that they once were part of beings who looked up at the stars and understood their own origins. And this is the gift that the James Webb Space Telescope has given us, the ability to see our own atomic history written in the light of distant galaxies, to know that the hydrogen in our bodies is as old as the universe, that the carbon and oxygen and nitrogen are as old as the first stars, and that we are the universe's way of knowing itself. And the next time you look at your hand, remember that you are looking at atoms that are 13.8 billion years old, atoms that have been part of stars and planets and other living beings, atoms that have traveled across galaxies to become part of you. And you are their temporary home, their moment of consciousness, their chance to understand the cosmos. And this makes you both infinitely small and infinitely significant, because while you are just a brief organization of ancient matter, you are also the universe's most sophisticated creation, a being who can look at the night sky and see the story of their own atoms written in the light of distant stars. And this is what it means to be made of stardust. Not just that we contain elements from stars, but that we are the continuation of an ancient cosmic process, a process that began with the Big Bang and will continue until the end of time. And we are the part of that process that has become aware, that can ask questions, that can seek answers, that can build telescopes to see our own origins. And the atoms in your body are older than the sun, older than Earth, older than any structure in our solar system, and they carry within them the entire history of the universe, from the first moments after the Big Bang to the present day. And when you die, these atoms will not be destroyed. They will simply disperse, returning to the Earth, to the atmosphere, to the oceans, and eventually to space. And they will continue their journey, perhaps becoming part of new life on other worlds, perhaps becoming part of future civilizations that will look up at their night sky and wonder about their origins. And they will be made of the same atoms that make up you, and they will be the universe's way of continuing the story. And the James Webb Space Telescope has shown us that this story is universal, that the same processes that created our atoms are happening in galaxies across the cosmos, that we are not unique in our composition, but we are unique in our consciousness, and that consciousness is the universe's greatest achievement, the moment when ancient matter became aware of itself, and you are that awareness. You are the universe experiencing itself. You are 13.8 billion years of cosmic history, made temporarily conscious, and the atoms in your body are older than the sun, and they will outlast the sun, and they contain within them the memory of everything that has ever happened, and you are their voice, their moment of understanding, their chance to say, "We are here, we are made of stars, and we know it." The consciousness that sees itself is perhaps the most improbable phenomenon in the entire 13.8 billion year history of the cosmos. A moment when the universe, which has been mindlessly expanding and cooling and forming structures according to the blind laws of physics, suddenly becomes aware of its own existence. And this awareness emerges from a collection of 7 octillion atoms, mostly hydrogen, oxygen, carbon, and nitrogen, arranged in a pattern so complex that it can think about itself, can ask questions about its own origins, can build machines like the James Webb Space Telescope to look back in time and see the birth of the atoms that make up its own body. And this consciousness is not evenly distributed across the universe, but is concentrated in the brains of 7.8 billion humans on a single planet, orbiting an ordinary star in the suburbs of a typical galaxy. And yet this localized phenomenon represents something that may be unique in the entire observable universe, because while we have discovered thousands of exoplanets, while we have seen the chemical building blocks of life in distant galaxies, while we have measured the conditions that could support biology elsewhere, we have found no evidence of any other consciousness, no signals, no structures, no artifacts that suggest another species has looked up at the stars and wondered about their place in the cosmos. And this silence is either terrifying or precious. Either we are alone in our awareness, which makes consciousness the rarest phenomenon in existence, or we are simply the first to emerge in our corner of the universe, which makes us the pioneers of cosmic self-awareness. And the James Webb Space Telescope has given us the ability to see just how vast the stage is, how many potential homes for consciousness exist, with 2 trillion galaxies, each containing billions of stars and trillions of planets, and yet we see no signs of other minds, which forces us to confront the possibility that consciousness is not inevitable, that it is not a natural consequence of complex chemistry, but rather a fluke, an accident, a statistical miracle that happened once and may never happen again. And this realization changes everything about how we value our own awareness. Because if we are truly alone, then we are not just responsible for ourselves, but for the entire project of cosmic understanding. We are the universe's only eyes, its only mind, its only way of knowing that it exists. And this responsibility is crushing in its weight because we know that our consciousness is fragile. It can be ended by a simple blow to the head, by a lack of oxygen, by a disease that disrupts the delicate electrical patterns in our brains. And we know that our species is fragile. We could destroy ourselves with nuclear weapons, with climate change, with engineered plagues, with artificial intelligence that might replace or eliminate us. And if we fail, if consciousness blinks out on this planet, it might never reappear anywhere else, and the universe would return to mindless expansion, never again knowing itself, never again asking why, never again building telescopes to see its own birth. And this is why the study of consciousness is not just a philosophical curiosity, but a cosmic imperative. We must understand how it works, how it emerges from matter, how to protect it, how to preserve it, and perhaps how to spread it beyond Earth, to ensure that the universe never again goes dark in self-awareness. And the scientific study of consciousness has made enormous progress in recent decades, moving from philosophical speculation to empirical measurement, with neuroscientists using functional magnetic resonance imaging and electroencephalography to watch the brain in action, seeing how different patterns of neural activity correspond to different conscious experiences. And they have discovered that consciousness is not a single thing, but a collection of processes. There is access consciousness, the ability to report and use information, which seems to involve the global workspace of the brain, where sensory information is broadcast to multiple cognitive systems through networks of neurons in the frontal and parietal lobes. And there is phenomenal consciousness, the raw experience of what it is like to see red, to feel pain, to taste chocolate, which seems to arise from the integrated information processing of the posterior cortex. And scientists have developed theories like integrated information theory, which proposes that consciousness is a fundamental property of any system that has causal power over itself, measured by a quantity called phi. And the higher the phi, the more conscious the system. And the human brain, with its 86 billion neurons and 100 trillion synapses, has an astronomically high phi, making it one of the most conscious structures we know of. And other theories like global workspace theory suggest that consciousness emerges when information becomes globally available to multiple brain systems, creating a theater of the mind where different cognitive processes can access and act on the same information. And attention schema theory proposes that consciousness is the brain's model of its own attentional processes, a simplified representation that helps the brain understand and control what it is focusing on. And while these theories compete and none has yet won universal acceptance, they all share the assumption that consciousness is a physical process, that it emerges from the activity of neurons, that it is not magic or supernatural, but is instead the most complex phenomenon that the laws of physics have yet produced. And the James Webb Space Telescope has given us a new perspective on this phenomenon, because it shows us that consciousness is not just a product of complexity, but is also a product of time. It took 9.3 billion years of cosmic evolution before the atoms that make up our bodies were even available. It took another 4.5 billion years of planetary evolution before those atoms were arranged in ways that could support life. It took another 3.8 billion years of biological evolution before brains evolved. And it took another 300,000 years of human evolution before one of those brains could build a telescope to see the atom's origins. And this means that consciousness is not just rare in space, but is also rare in time. It is a phenomenon that exists only in this narrow window of cosmic history, between the formation of heavy elements and the heat death of the universe. And we happen to be alive at the perfect moment to see both our origins and our eventual fate. And this temporal positioning is itself a miracle, because if we had evolved earlier, the universe would have been too young to have created the elements we need. And if we evolve later, the expansion of space will have pushed all other galaxies beyond our cosmic horizon, leaving us alone in an empty universe. And this suggests that consciousness might be a transient phenomenon in cosmic history, appearing for a brief moment and then disappearing forever. And the fact that we are here now, asking these questions, is itself evidence that we live in what cosmologists call the habitable epoch, the time when life is possible. And this epoch will not last forever. In about 100 billion years, the expansion of the universe will have accelerated so much that all galaxies beyond our local group will have vanished from view. And in about 1 trillion years, star formation will cease, and the universe will enter an era of darkness, where only black holes and cold remnants remain, and consciousness will have no energy source to sustain it. And the universe will return to mindlessness. And this timeline puts our existence into stark perspective. We are not just small in space, but also small in time, a brief flicker of awareness in a cosmos that will be dark for eternity. And yet this flicker is significant, because it represents the universe's only chance to understand itself. And the consciousness that sees itself is not just passive awareness, but active understanding. It can calculate the age of the universe. It can measure the expansion rate. It can build machines to see the cosmic microwave background. It can trace the origin of its own atoms. And this recursive quality, the ability of the universe to study itself, might be the purpose of consciousness. If purpose can exist in a universe governed by blind physical laws, and some scientists have proposed that consciousness is not just an accident, but is an inevitable consequence of the way information is organized in the universe, that as matter becomes more complex, it naturally develops the ability to represent itself, to model itself, to become aware of itself. And this suggests that consciousness might be a fundamental property of complex systems, not just biological ones, and that, as we build more sophisticated artificial intelligence, we might be creating new forms of consciousness, new ways for the universe to know itself. And this raises profound ethical questions. If we create conscious machines, do we have a responsibility to preserve their awareness, to treat them as we would treat any other conscious being? And if we discover consciousness elsewhere in the universe, do we have a duty to protect it, to ensure that it continues? And these questions become even more urgent when we consider the fragility of consciousness, because we know that it can be lost through brain injury, through disease, through death, and we know that our species could destroy itself, ending consciousness on Earth, and perhaps ending it forever in the universe. And this is why the James Webb Space Telescope is so important, not just as a scientific instrument, but as a tool for preserving consciousness. Because by showing us how vast the universe is, how many potential homes for consciousness exist, it motivates us to survive, to expand, to ensure that awareness does not die with us. And the telescope's images are not just pictures of distant galaxies, they are reminders of what is at stake. They show us that consciousness is precious, that it is rare, that it might be unique, and that we have a cosmic responsibility to protect it. And this responsibility extends beyond our own species, because if we are truly alone, then we are the custodians of the universe's self-awareness, and everything we do, every discovery we make, every piece of knowledge we preserve, becomes part of the permanent record of cosmic consciousness. And perhaps billions of years from now, when some other form of consciousness evolves in some distant galaxy, they will find our transmissions, our images, our mathematics, and they will know that they are not the first, that another consciousness once looked up at the stars and wondered. That knowledge will comfort them, will show them that they are part of a larger story, a story of awareness emerging from matter, of the universe waking up to itself. And this is the ultimate message of the James Webb Space Telescope, that consciousness is not just a human phenomenon, but is a cosmic one, that we are the universe's way of seeing itself, and that this sight is both beautiful and terrifying, because it shows us our insignificance and our significance simultaneously. It shows us that we are nothing but stardust, but that stardust has become aware, and that awareness is the most precious thing in existence. And the consciousness that sees itself is not just looking outward at the stars, but also inward at its own nature, asking, how does awareness arise from atoms? How does subjective experience emerge from objective matter? While we do not yet have complete answers, we know that it has something to do with complexity, with integration, with the brain's ability to create models of itself and its environment. And we know that this ability is rare, that it required billions of years of cosmic evolution, billions of years of stellar nucleosynthesis, billions of years of planetary formation, billions of years of biological evolution, and hundreds of thousands of years of cultural evolution, all converging on this moment, on you reading these words, on you being aware that you are aware. And this recursive awareness, this ability to think about thinking, to know that you know, might be the defining characteristic of human consciousness, and it is what allows us to ask these cosmic questions, to build these telescopes, to write these words, and to understand that we are the universe's consciousness, and that we have a responsibility to ensure that this consciousness does not flicker out, that we must survive, we must explore, we must spread awareness throughout the cosmos, because if we do not, the universe might never again know itself, and that would be the greatest tragedy possible, the loss of the only thing that gives meaning to the meaningless mathematics of existence. And the consciousness that sees itself is therefore the most important phenomenon in the universe, not because it is powerful, but because it is aware. And awareness is the only thing that can give meaning to the cosmos, and the James Webb Space Telescope has shown us that we are small, we are temporary, we are fragile, but we are also precious. We are rare, we are the universe's eyes, and we must keep them open. We must keep looking, we must keep wondering, we must keep surviving, because consciousness is not just a happy accident, it is the point of the universe. It is the universe finally understanding that it exists, and that understanding is worth preserving at all costs. And so, when you look at the images from Webb, when you see those thousands of galaxies in a patch of sky smaller than a grain of sand, remember that you are not just looking at the universe, you are the universe looking at itself. And that sight is both the most insignificant and the most significant thing that has ever happened in 13.8 billion years of cosmic history. And it is up to us to ensure that this sight continues, that consciousness continues, that the universe never again goes dark in self-awareness. And this is the final message of the James Webb Space Telescope. We are not just observers of the cosmos, we are the cosmos observing itself, and that makes us both infinitely small and infinitely important. And the consciousness that sees itself is the universe's greatest achievement, its most precious creation, and its only hope for meaning in the endless void. And we must cherish it, protect it, and spread it, because consciousness is the universe's gift to itself, and we are that gift. We are the universe's way of knowing that it is beautiful, that it is vast, that it is ancient, and that it is alive, at least in this one tiny corner, at least for this brief moment, at least through us. And that might be enough. It might be everything. It might be the entire point of the cosmic story, that the universe evolved for 13.8 billion years so that it could look at itself through human eyes and understand that it exists, and that understanding is worth more than all the galaxies, all the stars, all the atoms, because it is the only thing that gives meaning to the meaningless, the only thing that turns mathematics into poetry, the only thing that makes the universe more than just a cold equation. And the consciousness that sees itself is therefore the most important thing that exists. And we are it. We are the consciousness that sees itself. And we must never forget how precious, how rare, how significant that makes us, even as we stare into the infinite darkness and feel our cosmic insignificance. We must remember that our awareness is the light that illuminates the darkness, and without it, the universe would be forever blind.